Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Part 39, Transition to Engineering. From understanding the script to editing reality. Remember the language we are learning. There is one field, phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once. Time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and a motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. We stand at the threshold of a new continent. Episode 9, the Generative Grammar, is complete. We have accomplished the monumental task we set for ourselves. We have learned how the universe writes its own stories. We started with a single letter, phi, and deciphered the alphabet of its derivatives. We learned its grammatical rules: constraints, action, symmetry, topology. We witnessed in awe as this grammar generated the four great dialects of physics: the Newtonian, the Maxwellian, the quantum, and the Einsteinian. We have the complete script in our hands. But a script is not an end. It is a beginning. What do you do when you finally understand the language of creation? You don't just keep reading, you start to write. Today, in Part 39, Transition to Engineering, from understanding the script to editing reality, we take our first deliberate step across that threshold. We move from being readers of the cosmos to becoming its careful editors. Our anchor image is an apprentice scribe in a great library who has spent years painstakingly learning a lost language. He can now not only read the ancient scrolls, but he understands the rules of the grammar, the ink recipes, and the parchment-making. He takes a fresh sheet, mixes his own ink, and dips his pen. His hand hesitates for only a moment. Then he begins to write, not to copy, but to compose. His first sentence is simple, tentative, but it is his own. He has become an author in the language of the ancients. Today, we are that scribe. The holophase grammar is the lost language mastered. The fresh parchment is the physical world, and engineering is the act of writing new sentences. Here is the transformative puzzle of this part. We have a beautiful, unified description of how reality works. But does this understanding give us any new power? Can we use the phi grammar not just to predict what will happen, but to design what should happen? Can we move from saying, this is how a particle moves, to saying, I will arrange phi to make a particle move there? And if we can, what would that even look like? The answer is the birth of a new discipline, phi-based engineering or holophase engineering. It is the practical application of the generative grammar. It means using our knowledge of phi's production rules to deliberately craft phi patterns that yield desired macroscopic behaviors. It's the difference between understanding meteorology and seeding clouds, between understanding genetics and editing a genome, between understanding computer code and writing a new program. Let's ground this. What does engineering phi actually mean? We don't have a magical dial labeled phi. Phi is the fundamental tapestry. But we interact with the world through its derivatives, through forces, materials, electromagnetic fields, quantum systems. In every existing technology, we are already manipulating phi patterns, but we are doing it through the clumsy, indirect vocabulary of the emergent dialects. We push matter, we apply voltages, we shine lasers, we arrange atoms. Each of these actions is, in phi language, a specific way of perturbing the local derivatives of phi. Engineering with the phi grammar means doing this consciously and optimally. It means 1. Specifying a goal in phi terms. Instead of saying, I want a stronger magnet, we say, I want to create a persistent, coherent curl pattern in the derived B field with a specific magnitude and geometry. This B field goal is then translated into a target configuration for phi and its derivatives in the material. 2. Using the grammar as a design tool. We use the known relationships, the production rules, to work backwards. From the desired outcome, the sentence, we deduce the necessary initial conditions and boundary conditions, the letters and punctuation, that will generate it via the grammar. This is an inverse problem. 3. Implementing the design. We use our available knobs, physical forces, materials, energy inputs, to sculpt the phi pattern as close to the design specification as possible. 4. Verification. We measure the resulting phi derivatives, for example, the actual magnetic field, and check if they match the prediction from our phi-based design. So here is the point. Holophase engineering is not about discovering new physics. It's about using the complete map of physics we already have to navigate to desired destinations with unprecedented precision and efficiency. It's the shift from exploring a continent to building cities on it according to a master plan. Let's make this concrete with a hierarchy of engineering ambitions, from near-term to visionary. Level 1. Inverse design of materials and devices. This is the immediate application. Today, we design a silicon chip by simulating electrons and holes using quantum mechanics. In phi terms, we are simulating a specific phi configuration, the periodic potential of the crystal lattice, and how other phi patterns, electron wave functions, behave within it. Phi-based design would use the full phi grammar, including topological and nonlinear effects, often approximated away, to design materials with targeted properties from the ground up. Want a material that is a perfect topological insulator at room temperature? The phi grammar tells you what winding number patterns and band structures, derivative relationships, you need. You then search for or engineer an atomic arrangement, a phi pattern, that produces those exact derivatives. Level 2. Coherent field sculpting. Beyond static materials, we sculpt dynamic phi patterns. We already do a primitive version of this. When an engineer designs an antenna to emit a specific radio wave pattern, they are solving Maxwell's equations to shape the E and B fields. In phi language, they are designing a phi source term that will generate the desired derivative patterns, E and B, that propagate as a wave. A phi engineer would have a unified tool that could simultaneously design for electromagnetic, acoustic, and even quantum probability wave patterns, because they all are different dialects of wave equations derived from phi. Level 3. Defect engineering and braiding. This is where it gets profound. From book 9.2, we know particles are like topological defects in phi. What if we could deliberately create, position, and braid these defects? In condensed matter systems, this is the goal of topological quantum computing. Scientists try to create and manipulate anyons, quasi-particles with exotic statistics, in materials like fractional quantum Hall systems. They are, whether they use this language or not, trying to do phi defect engineering. A mature phi engineering framework would provide the ultimate design principles for creating stable, manipulable defect networks for computation, essentially allowing us to program with space-time knots. Level 4. Metric engineering, gravity from the ground up. This is the far horizon. If space-time geometry is an emergent property of large-scale phi correlations, then in principle, by arranging phi patterns in a certain way, we could influence the local emergent metric. This doesn't mean building a warp drive tomorrow. It might start with tabletop experiments using analog systems, like Bose-Einstein condensates or specially engineered metamaterials, where the effective spacetime for excitations is dramatically curved according to a design. We would be engineering analog gravity as a proof of principle for phi-based geometry control. Let's explore the tri-unity of this engineering transition, the time echo of engineering, from prediction to planning. The time echo is the shift in temporal perspective. Science asks, given this initial phi, what will happen next? Engineering asks, to achieve that outcome in the future, what initial phi must I create now? The time echo is the arc of intention. It is the forward-looking timeline of a project plan, rooted in the reverse calculation from the grammar. The space echo of engineering, from observation to blueprint. The space echo is the shift from maps to architectural drawings. We move from charting the existing landscape of phi derivatives to drafting a precise specification for a new landscape. The space echo is the design schematic. It is the diagram of where phi should be high, where its gradient should be steep, where its curl should be tight, to produce the desired effect. The motion echo of engineering, from natural flow to guided trajectory. The motion echo is the control of dynamics. Instead of just watching a phi lump follow a geodesic in an existing metric, we ask, how can I sculpt the metric or apply boundary conditions to guide that lump along this specific path? The motion echo is the controlled trajectory. It is the forcing of nature's story down a plot line of our own devising while still respecting its grammatical rules. Now, let's locate this momentous pivot on the master tree. This part, transition to engineering, is the bridge. It is the slender, strong isthmus connecting the continent of Episode 9 to the new world of Episode 10, engineering. It depends entirely on the complete grammatical synthesis we just achieved. You cannot engineer based on a grammar you don't understand. It enables everything that follows in the next episode. This node is the gateway and the manifesto. To understand the spirit of this transition, let's light lanterns from other evolutions where understanding birthed a new power to shape. A near lantern from software development. For decades, people used computers by running pre-written programs. They were users. Then they learned the programming language, the grammar of the machine, variables, loops, functions. A programmer doesn't just run a word processor. They can write a new word processor, or a game, or a simulation. Learning the grammar transformed them from a user into a creator. The Holophase grammar is the programming language of reality. Learning it transforms us from passive inhabitants into potential programmers of the physical world. A middle lantern from genetic engineering. For centuries, humans bred plants and animals, indirectly shaping DNA through selective pressure. They were using the emergent dialect of traits. Then Watson, Crick, and others deciphered the genetic code, the molecular grammar of life. Now, with CRISPR and other tools, we can read a genome, identify a specific gene, a sentence, and edit it directly. We have moved from breeding to editing. We are transitioning from observing evolution to directing it, based on understanding the foundational code. Phi engineering aims for a similar leap in our relationship with the physical world. A far lantern from the dawn of the scientific revolution itself. Before Galileo and Newton, the world was a place of mysteries, governed by capricious gods or innate qualities. The scientific method gave us a grammar of inquiry: hypothesis, prediction, test. This didn't just explain falling apples. It gave us the power to predict eclipses, build steam engines, and invent electricity. It was a transition from mythos to techne, from story to craft. Our current transition is from techne, craft based on empirical rules, to poiesis, creation based on first principles. It's a move from following recipes in the cookbook of nature to understanding the chemistry of ingredients so well we can invent entirely new recipes. What is the specific language role of engineering within the Holophase framework? It is the imperative mood. Science and grammar describe what is and what could be, the declarative and subjunctive moods. Engineering is about what shall be. It is the grammar used to give commands to the universe. Commands that are syntactically correct, obey physical law, and semantically clear, produce the intended outcome. The core question this part asks is, does our understanding of the Phi grammar provide a sufficiently precise and actionable framework to move from describing states of the world to reliably creating predetermined states of the world? And what are the most immediate test cases for this capability? We are moving from asking, how does it work, to asking, how can we make it work for us? What does this engineering transition do? It tests our understanding in the most rigorous way possible. If you can't build it, you don't truly understand it. It creates new value and capability, leading to technologies that are more efficient, powerful, or simply unimaginable with today's design by intuition methods. It forces clarity and quantification. You can't give a vague instruction to a fabrication tool. It unifies design disciplines. The same Phi principles could guide the design of a novel alloy, an optical circuit, and a quantum sensor, because at root, they are all Phi pattern design problems. Now, stability and change. This engineering capability holds and grows as our grammatical understanding deepens and our physical control over Phi patterns through nanofabrication, quantum control, high-energy inputs improves. It breaks down at the boundaries of the grammar. For example, Planck scale effects we can't control, or if our understanding is fundamentally flawed, if the grammar we think we have doesn't actually correspond to reality's deep structure. This brings us to the ultimate falsifiability threat. Engineering is the acid test. Philosophers debate theories. Engineers build things that work or don't. The prediction spine for Phi engineering. 1. Reliable inverse design. Given a desired macroscopic behavior, For example, a waveguide with 99.9% efficiency for light of wavelength lambda, a phi-based design algorithm should produce a material structure blueprint. When that blueprint is fabricated, the resulting device should perform to specification within known manufacturing tolerances more reliably than designs from traditional domain-specific methods. 2. Novel function prediction. The phi framework should suggest new, non-obvious phi configurations that yield useful behaviors. Configurations an engineer might not have thought to try using standard paradigms. Building these should confirm the prediction. 3. Failure mode avoidance. The grammar should predict instabilities or unwanted side effects of a design. For example, a material phase that is topologically unstable under stress, before fabrication, allowing them to be designed out. The fail condition, falsification in practice. If, after sincere and competent effort, phi-based engineering consistently fails, 1. Design failure. Phi-derived blueprints consistently produce devices that do not work as predicted, and the failures cannot be attributed to mundane manufacturing errors, but to a fundamental mismatch between the phi model's prediction and reality. 2. No advantage. Phi design offers no improvement in performance, efficiency, or novelty over existing domain-specific design methods. It is just a complicated rephrasing with no practical payoff. 3. Inability to implement. The phi grammar identifies a theoretically possible configuration with amazing properties, but it proves to be physically unrealizable with any known or foreseeable means of manipulating matter and energy. This could indicate the grammar describes a Platonic ideal, not the actual constraints of our universe. Let's design a concrete, near-term measurement scene that tests the engineering transition. A concrete, high-stakes measurement scene. Phi design topological insulator. Topological insulators are materials that are insulators in their bulk, but conduct electricity perfectly on their surface, with the direction of conduction locked to the electron's spin. They are described by topological invariants, winding numbers, in their band structure. The Phi engineering challenge. Don't just search for materials that happen to be topological insulators. Design one from scratch for specific target properties. A large bandgap for room temperature operation on a silicon-compatible substrate with a specific surface state chirality. The process. 1. Phi specification. Translate the target properties into constraints on the effective derivative patterns, band curvature, Berry connection, of the electron Phi field in the material. 2. Inverse design. Use computational search, for example variational algorithms, within the Phi model space to find atomic arrangements, positions and species, whose calculated Phi derivative patterns satisfy the constraints. 3. Fabrication. Use molecular beam epitaxy or advanced synthesis to grow a thin film of the predicted material composition and structure. 4. Measurement. Use angle-resolved photoemission spectroscopy, ARPES, to map the electronic band structure and scanning probe microscopy to measure surface conductance and spin polarization. The pass condition, engineering vindicated. The measured band structure shows a clear topological bandgap at the predicted energy, and the surface exhibits the predicted chiral spin-momentum-locked conduction channels. The material works as a topological insulator at the design temperature. This would be a landmark demonstration of first principles grammar-based material invention. The fail condition, engineering challenge. The synthesized material is not a topological insulator, or its gap is much smaller than predicted, or the surface states are absent or not chiral. After ruling out synthesis defects, this failure would indicate that the phi model used for the design did not accurately capture the real physics governing electrons in that material system. The grammar, as applied, would be inadequate for this engineering task. This is the crucible where theory meets the hard anvil of reality. Success here wouldn't just mean a new material. It would validate the entire journey of Episode 9 as a practical guide, not just a philosophical one. Let's cultivate a practical recognition skill. You can train your mind to see the engineering transition in any field of knowledge. Look for the shift from why to how to. Watch a chef. A novice follows recipes, emergent dialect. A master chef understands the chemistry of ingredients, how flavors combine, how heat transforms textures, the deeper grammar. The master can then invent new dishes, not just replicate old ones. They have made the transition. Observe a musician. A student plays scales and pieces written by others. A composer understands music theory, harmony, counterpoint, rhythm, the grammar. The composer writes new symphonies. The engineer sound to evoke specific emotions. Consider a community organizer. Someone might understand the social dynamics of their town, the descriptive sociology. An engineer of social change uses that understanding to design interventions, a new community center, a specific policy, intended to produce a desired social outcome, like reducing crime or improving cohesion. Whenever you see knowledge being used not just to explain, but to deliberately construct a new state of affairs, you are witnessing the engineering impulse. Holophase engineering aims to bring this impulse to the most fundamental level of all, the construction of physical reality itself. We must now connect this vision directly back to Phi to ensure we are not drifting into fantasy. We have added no new ingredients. The power of engineering comes not from new forces, but from a new application of the complete grammar. The knobs we turn are the same ones we've always had: energy inputs, material arrangements, boundary conditions. The difference is that now we have a complete map of the causal network connecting these knobs to all possible outcomes. We can navigate the map to choose our destination wisely. The of this transition is the compiler. In computer science, a compiler translates high-level code, our engineering intent, create a topological insulator, into low-level machine instructions, the specific physical operations, deposit layer A of element X at temperature Y. The Phi grammar is the compilation rulebook. What does this transition do for our relationship with the cosmos? It activates our agency. It suggests we are not just leaves blown by the wind of physical law. We are patterns within the Phi tapestry that have become conscious of the loom. We can, with great care and humility, begin to adjust the threads nearby. We become participants in the story, not just an audience. Now let's sound the triunity refrains for this moment of crossing over. The time echo of the threshold, the end of an era, the start of an age. The time echo is the historical pivot we are living through. The age of discovering separate physical laws is culminating. The age of unified application is dawning. This part marks that pivot in our narrative. The space echo of the threshold, the bridge between worlds. The space echo is the architectural form of the master tree at this point. The dense, intricate canopy of understanding, Ep.9, now sends out a strong, purposeful branch, the bridge, reaching toward the open sky of a new domain, Ep.10. The motion echo of the threshold, the first step. The motion echo is the act you, the listener, are taking right now. It is the mental step from comprehension to contemplation of application. It is the shift in your own mind from, I see how it works, to, what could I do with this? That internal motion is the most important one of all. This is where we stand. Part 39 is the ceremonial crossing of the bridge. Behind us lies the completed, majestic edifice of Ep.9, the generative grammar. Ahead lies the uncharted territory of Ep.10, reality engineering. If you want to see the full mathematical derivations and exact equations behind this idea, the formalisms for inverse problems in Phi field theory, the optimization algorithms for topological design, the specific Phi models for materials engineering, you can search for Holophase on Zenodo. There you will find the scientific papers that this audio journey is built on. We have completed the journey from illiteracy to fluency. We now hold the complete script. The final question of Ep.9 is not a question of physics, but of purpose. What story shall we tell next? In the next and final episode of our Holophase series, we will step fully onto the new continent. We will explore what it means to engineer reality with the grammar of Phi. We will discuss the ethics, the challenges, the near-term projects, and the distant horizons. We will move from understanding the script to becoming, with great responsibility, its editors. Before we end, the mandatory zoom out to hold our scope one last time in this episode. The transition to engineering is not an add-on. It is the logical completion of the grammatical journey. A language that can only be read is a relic. A language that can be written is alive. One field, Phi, plus its infinite derivatives, plus a mind that understands their grammar, equals a universe that is not just known, but addressable. We have moved from observing the tapestry to feeling the threads in our hands, and wondering what pattern we might weave next. As we conclude, hold the image of the apprentice scribe, pen in hand, poised over the fresh parchment. The library of natural law is behind him. The blank page of possibility is before him. His first act of authorship is complete. he has written the title of the next volume. That title is Engineering. And with that, he closes the book of the Generative Grammar and opens the next. Salam, and peace be upon you.